Hey there, here is your video on these formulas for chapters 17 and 18. So the first one here is delta G equals delta H minus T delta S, perhaps the one we should really know how to use. We could also add the little degree symbol for standard conditions, which would be 25 degrees Celsius, 1 atmosphere, 1 mole per liter solutions. Whereas without that symbol, it means non-standard. So what would we use it for? Well, calculating delta G, given delta H and delta S. One thing to keep in mind is that typically delta H is in kilojoules per mole, while delta S is in joules per Kelvin mole. So you would have to convert either your kilojoules per mole to joules per mole or joules to kilojoules, remembering that a kilojoule is 1,000 joules. So with the temperature, you can see how multiplying the temperature here, let me just put the minus in, would have to be in Kelvin. Hopefully that's pretty obvious. Now, so you could calculate delta G, and just a friendly reminder that when delta G standard is less than 0, that reaction is spontaneous as written in that forward direction. If delta G is positive, standard delta G, then the reverse reaction is spontaneous. The forward reaction is not spontaneous. So speaking of spontaneity, another thing we should remember is the scenarios. Oh wow, that's big, isn't it? Let's make it smaller. So let's do this. We're going to write our delta G equals delta G standard equals delta H minus T delta S, and we'll go through each of these scenarios in the order listed here. So starting with delta S positive, delta H negative. So delta S positive, delta H negative. Because we subtract T delta S, we end up with minus and then minus plus. So minus, I'm just going to call that plus minus. So we have delta G equals minus plus minus or negative. So in that case, it doesn't matter what the temperature is, it is spontaneous at all temperatures. So another way to think about it is delta H is negative, and that means delta S of the surroundings is positive, and delta S system is positive. So both the surroundings and system delta S is positive, meaning it's always spontaneous. Let's look at the next one. Delta S is positive, this one down here. Delta S positive, delta H positive. Okay, so we're going to erase this, and let's just go like that. So both positive. Now we can look at delta H, and that's not favorable for spontaneity. So if we bring it down, we have a plus, minus a plus, or we'll call it plus a minus. This one would be temperature dependent. So we can think about that. If the temperature is low, in fact, what if it were 0 Kelvin? This term would not be here at all. That would mean delta G is equal to delta H. And if delta H is positive, then delta G is positive, not spontaneous. So since I drove it all the way to 0 Kelvin, that tells us that low temperatures, it's not spontaneous. So it is spontaneous at higher temperatures, above a particular temperature. And that is exactly what it says here, spontaneous at high temperatures. So that is when both delta H and delta S are positive. Now we're going to erase this again and look at the next scenario in which delta S is negative and delta H is negative. In this case, delta H is negative. Again, that's good for spontaneity. Delta S is negative, that's bad for spontaneity. So in this case, if we take minus for delta H, and then we have minus negative, so that's really plus a positive. we can see that the enthalpy term is now favorable, but the entropy term is bad. So again, if we say drive this to the lowest possible temperature, 0 Kelvin, then delta G would equal delta H. And if delta H is negative, then delta G is negative. So basically, this would be spontaneous at low temperatures, below a certain temperature. And we'll talk about that next, about predicting what that temperature is. So spontaneous at low temperatures when delta H is negative and delta S is negative. So at higher temperatures, that unfavorable entropy term will overtake. So in other words, if we can imagine this plus right here from the unfavorable entropy term is much bigger in magnitude than the plus is much bigger than the minus, then delta G would be positive, and that's meaning it's not spontaneous. Again, you can pause this, speed it up, slow it down, whatever you like. Final scenario, delta S negative, delta H positive. Yes, it is never negative, never spontaneous. And that is why we say it is not spontaneous at any temperature. Now, speaking of temperatures, and this would apply to only these two scenarios that are temperature dependent. We can calculate that temperature when the spontaneity changes from, say, being not spontaneous to spontaneous. So just to give examples, usually include state changes. So we had done one in class, I want to say for the boiling point of bromine maybe. But if you take that delta G equals delta H minus T delta S, and we want to know, the question is something like what temperature is the boiling point or something of some particular substance. What is the boiling point? Or what is the freezing point? Or what temperatures, so we could say a range, and then we would have an inequality on our hands. At what temperatures is something, let's just say change, spontaneous? In both cases, what we would do is we would set delta G equal to 0. And specifically, if you wanted to know when is the change spontaneous, rather than say 0 equals delta H minus T delta S, we could say, I'm going to flip both sides, delta H minus T delta S, when is that less than 0, right? Because that would be spontaneous. So if you wanted to know, above which or below which temperature, you would set delta H minus T delta S to be less than 0. That means that's delta G, and below 0 negative is when it is spontaneous. Because that's an inequality, I would put the numbers in first, which usually students like to do, and then solve for T, and you would end up with, depending on the sign of delta H and delta S, it would be greater than or less than. If you use this version, and we just want to know what's the boiling point or something, then just solve for T equals, and again, that's going to turn out to be in Kelvin, but maybe we want it in degrees Celsius, something like that. Okay, so bottom line is, if there is something about a temperature, it sounds like it's spontaneous above a certain temperature or below a certain temperature, you're going to set your delta G to 0. Okay, all right. That's a lot to do with that first formula. It won't take up that much time with the other formulas, believe me. So looking at the next one, this basically allows us just to simply convert between K, the equilibrium constant, and delta G. That's all. And we can also relate these two in another way. If delta G is, standard delta G is less than 0, then K is large. If the standard delta G is equal to 0, K equals 1. And if delta G, now I'm encroaching on this next formula. If delta G is greater than 0, then K would be between 0 and 1, or a fraction. So examples include a strong acid for a large K. Not really any obvious example of delta G equals 0, but a weak acid is a good example of delta G being positive. Now you might ask yourself, hey, when we put a weak acid into solution, doesn't it still dissociate a tiny little bit and move to the right? Because K is greater than 0, but it's a tiny number. And that is true. It does move to the right, but that doesn't mean it, when we use standard concentrations. So if we had just, for example, let me go all the way to the right over here. Let's say we had a weak acid such as HF. Okay, we've got a weak acid. And I want to say its Ka is somewhere around 10 to the negative 4 off the top of my head. So anyway, that dissociates into H plus A minus. Okay, I gotta scroll here, so I'm not hitting those bars there. Okay, so if we start with, say, 1 molar HF, and these are 0 right here, indeed, it's going to move to the right. But those are not standard concentrations, right? So if we put in standard concentrations, which is 1 mole per liter here, 1 mole per liter here. So if we start with all concentrations standard, right, that's what that delta G means, is the standard delta G means 25 degrees, all concentrations are 1 mole per liter. This is not going to move to the right. It's not spontaneous in the forward direction. It is spontaneous in the reverse. Oops. It's spontaneous in the reverse direction. Let's do this. Let's cross this out with red. So in other words, if you take, say, a strong acid and a conjugate base and then HF, all of the same concentration, it's going to move to the left, not the right. So bottom line is this formula allows you to interconvert between delta G and the equilibrium constant. All right, on to the next one. This basically relates the delta G to the cell potential, where N is the number of moles of electrons transferred, which you would obtain from the redox equation. For example, the copper-zinc cell, copper 2+ plus zinc, yields copper metal plus zinc 2+. That one involves 2 electrons, so that would mean N is 2 moles of electrons. Faraday constant is the 96,485. It is the charge of 1 mole of electrons. Okay, and then E is the whatever standard potential in volts. Now we also remind ourselves that a volt is a joule per coulomb. So if we just put our units in here, we have moles of electrons. The Faraday constant is coulombs per mole electrons, if I can squeeze it in. And then instead of volts, we're going to put joules per coulomb. We can see that the coulombs cancel, the moles of electrons cancel, and we end up with joules, which would make sense for delta G. So again, if you have the standard cell potential, you can get the standard free energy difference. If you have the free energy, you can get the cell potential. That can even be used in other ways. Even if it isn't a redox, it technically doesn't have a standard potential. All right, on to the next one. This is the beloved Nernst equation, which allows us to calculate the cell potential given the standard cell potential and then these other variables. So R is our 8.314 joules per Kelvin mole. By the way, same R right here for delta G equals minus RT natural log K. Temperature in kelvins, and again moles of electrons, Faraday constant, that sort of thing. But I think let's take this formula over here. we're just going to keep going like this. Or so I thought. So again, that is E equals standard E minus RT over NF natural log Q. Now, if we are to take our, let's go back to our zinc copper cell. So zinc, zinc plus copper 2 to zinc plus zinc 2 plus. Zinc is oxidized. Copper 2 is reduced to copper metal. So Q would be, I didn't put phases on, but the metals are solids and the ions are aqueous. Remember, some redox reactions have acid in them. Those would be in solution. H plus would be in solution. But just like K, we don't include solids. So it's products over reactants, the reaction quotient to the power of the coefficient. So in this case, there are all the coefficients are 1. So it is simply zinc 2 plus divided by copper 2 plus. That would be Q. So one way to think about it is if Q is equal, let's start with greater than 1. Q is greater than 1. If we put a number greater than 1 in for Q, then we get natural log of a number greater than 1, which is a positive number. So we end up subtracting the standard potential minus RT over NF, that's all positive. And then since Q is positive, natural log of Q is, as Q is greater than 1, natural log Q is positive. So we get a positive number we subtract from the standard potential. So what that means is the cell potential is less than the standard cell potential. So this would be like if we have more products than reactants. That would be like the reaction is proceeding to the right, so there are fewer reactants and more products. So we could say it is closer to the equilibrium position. It's not yet there because E is still not 0. It is less than the standard potential if Q is greater than 1. If Q were less than 1, specifically between 0 and 1. So for example, if Q were, let's say, 0.1, we did this in the lab. In that case, we would have natural log of a number less than 1, which would make that term negative. And so now we would have this whole term RT over NF times natural log Q would be negative. So we would have E minus a negative, or E standard E plus a positive. So the cell potential is what we're calculating here, if that wasn't clear. The cell potential, the non-standard cell potential, would be greater than the standard cell potential. Okay, so this would be, again, happening if we had fewer products compared with the reactants. So you had more copper ions in solution versus zinc. The cell potential is greater than the standard cell potential. And then finally, we could say if, I guess I should have started with this, but if Q equals 0, then we have natural log of 0. That's not right. Sorry. If Q is 1, not 0. You can't take a log of 0. So if concentration of products over reactants was 1, so 1 over 1, for example, Q would be 1. Natural log of 1 is 0, and then the potential would equal the standard potential, which is reminding us that standard reaction conditions are 1 mole per liter of anything in solution. If this were gases, which is not really relevant for these solution electrochemical cells, they would be 1 atmosphere in pressure. Now, one final way to look at this formula, if I can get rid of this highlighting, nope, took the Q out, is as we went as it came up in class, if Q is equal to K, that's equilibrium, the cell potential is 0. And when we did that, if we plug in 0 for E, we end up with this formula. Where do we go with this? How about to the right? All right, so we're going to put in 0 for E and K for Q. So we get 0 equals standard cell potential minus RT over NF, natural log Q, no, natural log K. And if I move things around, E would be equal to RT over NF, natural log K. And I'm pretty sure this formula is written over there already. This is a way to interconvert between a cell potential and an equilibrium constant. In this case, it is solved for cell potential. So if you know your equilibrium constant, natural log times RT over NF. You've got to know N, the number of moles of electrons in that redox reaction. That gives you your cell potential. Conversely, if you solve this for K, so that's going to be an exponential. K equals E to the NF over RT. If we solve that, I'm going to let you do it on your own. In that case, if we have, am I missing anything? E. I'm missing E times E. So we'll put E right up in there. There we go. There's no negative sign, despite what you might think. This gives you the equilibrium constant if you know the cell potential. So pick any two half reactions in table 18.1, reverse the lower potential half reaction, change the sign of that potential, add those two half reactions together, making sure the number of electrons are equal, and then add the two cell potentials. And if you plug that cell potential in here with N, F, R, and T, you get an equilibrium constant for that electrochemical cell. So that is actually down here, which we just talked about, this one right here. So the cell potential as related to the equilibrium constant. The last two equations are quite simple to explain. You can only use these at 298 Kelvin or 25 degrees Celsius. It has been simplified. It's a simplified version of the Nernst equation that operates only at 25 degrees Celsius or 298 Kelvin. So if your temperature is anything but 298 Kelvin, then you need to use this first equation. If it is 298 Kelvin, you need to use the second one. One thing to note, there's no unit in here. You can just note that the unit of this whole term here that you're subtracting is volts, because you're going to have standard potential in volts minus all of this will end up to be volts. You could say there's a unit inside that for this 0.0591 because N is moles of electrons, but we don't need to work it out if we know that that all is going to make volts. So that's an easier version. One other thing to note is this version at any temperature uses natural log. This one uses log base 10. So be careful if you want to switch versions. And similarly, this is the equation to interconvert the standard potential and K, but again at 298 Kelvin only. Whereas this one, all temperatures would work. And that's how you use those formulas.